Hi guys, so in this video we're going to be going over some practice problems with transforming trig functions. So I've got this function in front of me, y equals 3 sine 2x minus 60 degrees plus 1. And we're going to be drawing this and going through the process of doing so. So I think the first thing we're going to say is that this video is going to be comprised of 3 different functions. We're going to have the sine, cos, and tan functions, so we just know how we can transform all of them. We're going to go through one example of each. So in the last video, we deduced that the general structure for a function, a trig function, is y equals a sine, I'm putting sine here, but it can be sine, cos, or tan, then b times x minus c plus d, where a is the amplitude, b is the period, c is the horizontal shift, and d is the vertical shift. So right now, this function isn't precisely in the right form because while we have the a and d parts down, the b and c are not very distinguishable, just because in the structure we have over here, the x is actually meant to have a coefficient of 1, while in this one it has a coefficient of 2. So we can factor out real quick, and we can get the function 2 times x minus 30 degrees instead, because we factored out a 2. So now we can start assigning our a, b, c, and d values to our specific example. So our a, which is our amplitude, in this case is 3. Our b, which is our period, is 2. So it will go through two cycles before it reaches 360 degrees, which is, well, we're going to do it from 0 to 360 degrees. And then c, which is our horizontal shift. So this one's counterintuitive. And while we think that because it's minus, it has to go to the left, it's actually going to the right by 30 degrees. 30 degrees right. I'm just going to draw a right arrow. And then our vertical shift, which is equal to 1 unit up. All right, so now I think what we're going to have to do is assign we're going to have to make some markings on our diagram by adding some intervals. So we know that it's minus 30 degrees, so it's being translated by 30 degrees. So that means that an appropriate interval within our x-axis would be every 30 degrees. Let's just mark those out. So this is 30 degrees, 60, 90. I'm just going to decrease the pen size, it's a bit thick. 120, 150, 180, 210, 240, 270, 300, then 330 is right there, and 360 is over here, and 0 is obviously over here. Okay, perfect. And the way we're going to do this is we're going to start by figuring out what order do we do these transformations in, because obviously we can't just do all the transformations in one go, or in a random order rather, because it could change the way we actually interpret the function. So we could start, I think what we should start off by doing is moving the function up by 1. So let's just get the plus 1 out of the way. So that means our principal axis is now y equals 1. So I'm going to draw that line over here for the principal axis. And we're also told that the amplitude is 3. So if we just draw the basic function, well, we should draw the top and bottom parts. So the top axis, which it will reach up to, is, well, it's 3 units above the principal axis, which is y equals 1. So that means the top it'll go to is y equals 4. This is the highest the function will go, because it'll go 3 on either side of the principal axis. Now, it'll go 3 below the principal axis as well, which means it'll go to minus 2 as its lower one. So we've drawn out our boundaries. Now we need to also understand the transformation is by 30 degrees. So what we can do first is draw our function without the 30-degree transformation. Let's just draw 3 sine 2x. So that means that the function is going to have to end one cycle over here and end another cycle over here. Let's just make those clear for now, because we're not including the transformation by 30 degrees just yet. So when you draw that function, well, you know that it's going to hit a maximum then at, well, sine usually hits a maximum at 90, but in this case, it's going to hit a 0 at 90 because everything is halved. At 45, it's going to be the one where it goes up to its maximum. And then meanwhile, at, oh, I just realized sorry, my bad. I actually forgot to look at the principal axis. The 0 is there. So we have a shape like this. And then 135 is where it's going to hit its minimum. So that will be at the bottom over here. And then 180 is when it goes back to the start. Then we can restart that cycle again. So 45 is 225 after 180. So that goes up here. Then 90 will be our 270 mark. Then 315 will be our 180 mark. And so on and so forth. And then we get back to 360. So this should be the function. Just drawing it out. So that should be our function without the transformation by 30 degrees. And now this is where you would do the horizontal shift. This is where it's most applicable. So I'm going to just draw this in red. So if everything shifts by 30 degrees, we can kind of just shift the points by 30 degrees. Because we've done all the other transformations except for the horizontal shift. And that one's just moving the points by 30 degrees. We're moving them 30 degrees to the right though. Which means that, for example, our 0 here at 0 degrees is actually going to be at 30 degrees instead. So we can move it over here instead. Then our maximum, which is at 45 in this case, is actually at 75. Then 90 will move over by 30 to 120. Then 135 will move over by 30 to 165. And then 180 will move over 30 to 210. Then our 225 will move over by 30 to 255. That goes here. Then our 270 will move over by 30 to 300. And so on. You kind of get the idea. Then 315 moves over to 345, which is over here. And then, of course, it finishes past 360, but it goes to 390. And we don't have 390 on this diagram. But likewise, I would also do the same thing from the left-hand side. Actually, points that weren't graphed before will make their way onto the diagram. So it will look something like this. Oops, let me just draw that left. Really, it would be a continuous one, but I can't seem to draw it well. So then you can see it goes off the page, and likewise, it goes over here. We don't know really how far it goes over there. So the point is that the red function is now our new function. So let me just erase everything else here. Oops. I'll leave the principal axis on there. 270. But let me just erase the other function, the black function. So it would look something like this. Yeah, you get the idea. This red function is 3 sine 2x minus 30 plus 1. And we can do it for other functions too. So it's just about making sure you get the right order and understanding what's logical. For example, the easiest thing would not be moving the horizontal shift immediately. I think it's firstly getting the general shape and then moving the whole function because it's much easier to visualize. So it's just about making this approach. But also, the easiest way to do it would just logically be using the green calculator using a table to graph each point, then connecting the dots. That's the easiest way if you have absolutely no idea of the shape, because oftentimes it gets very hard to visualize them, especially when you're also using radians, which we're covering in the next video. So let's move on to the next example. So our next function is going to be of cosine, and the function we have is y equals 2 cos of x plus 90 degrees plus 2. So because the coefficient of x is just 1, we don't have to factor anything out, and we can just identify our a, b, and c. So our amplitude, which is our a, is 2. B is the coefficient of x, which is, it's the factored part of the brackets, which actually is just 1, because nothing's factored. Then c is the horizontal shift, which is 90 degrees to the left. So I'm going to draw the arrow going to the left, because of course it's counterintuitive. So while plus usually means going to the right, in this case it means going to the left. And d is 2 units up. So the first thing we're going to do is we're going to get the plus 2 out of the way. So we're going to graph it with d already accounted for. So we're going to draw the principal axis at y equals 2. And we know from there we can draw the amplitude, because the amplitude is 2 units up and below. Well, in this case, it's 2 units up and below the principal axis, which is y equals 2. So our maximum is going to be 4 and our minimum is going to be 0. So, well, what we know of a cos function is that at 0, we're at our maximum, and then at 90, we're at 0. Then 180, we're at our minimum, which is 0. Then 270 and 360. So this would be 2 cos x plus 2. We haven't accounted for the vertical translation yet. So what we should do is move each of the points to the left by 90 degrees. So this point over here, so actually this point will go off the, this point will go off the screen. But then this point will move to 0. 180 will move to 90. I'm going to draw in a different color actually. Let's do it in red. Let's move off the screen. This 90-degree point will go to 0. 180 goes to 90. 270 goes to 180. Oops, I'll just draw that there. Then the 360 goes to 270. And, well, we would have to extrapolate from there. So we know that 450 would actually go back to the principal axis. So we're going to say that 360, therefore, because in a normal cosine curve, cos of 450 would go back to the principal axis, but in this case, it's going to be cos of 360, since 360 plus 9 gives you 450. And basically, now we can join the points up. So having moved all the points and implemented the translations and transformations, the curve looks something like this. And this is the cosine curve. It looks different from the sine curve in that it starts at a different point, but in reality, they're the same curves. That's why this one was so easy to graph. But however, we will now go on to our tangent function, because that's definitely a little bit different from sine and cosine. Okay, so on to our last example, which is with tangent, our final function. So we've got y equals tan of 2x minus 90 degrees minus 2 as our function. First thing we're going to do is we're going to actually write this in the same form as the first function, which factored out the coefficient of x to ensure that the period and the horizontal shift were distinguished. So we're going to write it as y equals tan of 2 times x minus 45 degrees minus 2. All right, so that's our function now, and we can identify our a to be 1, that's our amplitude, b is 2, c is 45 degrees to the right, since it's counterintuitive, and d is 2 units down. All right, so 2 units down, we're going to start with that. So let's draw our principal axis right there. So that's -2. And let's now move on to the asymptotes. So this is a part that we didn't cover in sine and cosine because tangent's the only one that has asymptotes, because it is defined as sine over cos. And when cos is 0, that's when it has asymptotes. So when do we know cos can be 0? Well, that's at 90 degrees. So that's going to be our first asymptote. And our other one's at 270 when we're looking at a 0 to 360 loop. All right, so those are our 2 asymptotes. However, when we think of the period, well, when you have cos 2x, we have to visualize cos 2x. That's the same as just doubling the number of asymptotes, because it means that it's going to hit 0 and more intervals. So therefore, doubling the number of asymptotes will also double the number of periods of the period of tan. So when we have cos 2x, the other times where it hits 0 is actually at 180, 360, and also 0, but only of the previous loop, somewhere at 180 and 360. Oops, let me just... It's also at 0, though, because from the other loop, you can think of 0 as the 360 of the other side. So it's at 90-degree intervals, in other words. So what does that mean? Well, now tangent's going to be showing up a lot of times in this cycle. So what about the values of 45, 135, 225, and 315? Let's graph those. Well, those are going to be the points where tangent is 0, or rather, it's 0 without the vertical shift. Because if you think about it, when you look at this factored part here, where we've written as tan of 2 of x minus 45. Well, that means if we wanted to make tan 0, well, tan 0 is equal to 0. And that means we're going to have to say that 2x minus 45 is equal to 0. So, sorry, 2x minus 45. So x minus 45 is equal to 0. So x is equal to 45 degrees. So that means that at 45 degrees, tangents at the principal axis. Wait, let me just get rid of that. Because, so even though at 45 degrees, the tan function itself is 0, we have a vertical shift of -2. So that means it's going to be sitting at -2 at 45 degree intervals. And now you might be thinking, well, what about the rest of the function? And in truth is, it depends on the other values of tangent. In general, the shape is going to be something like this. Just repeatedly over and over again. So that's the tangent shape. It's not actually as complicated as it may sound to draw. It's just about identifying the key points. In this case, 45-degree intervals made the most sense. And if you know the general shape is like that, whereas sine and cos are like this, then you're actually good to go. You just need to know the general shape after you've gotten a few points nailed down and you've identified your A, B, C, and D. So that's going to be it for this video. I hope everything made sense. If you don't understand something, please let me know in the comments. But that should be enough to understand how to transform different trigonometric functions with relative ease. And obviously, you can always fall back on your calculator to just graph all the points individually and then connect the dots if need be, because you will have your green calculator at all times. So thank you so much for watching the video, and see you in the next one.